Okay, welcome back to the second day. It's a great pleasure to open the second day with Andrej Bauer from the University of Ljubljana, who will inform us how to use excluded middle safely.
Thank you. Thank you for the invitation. It's a great pleasure to be here and to celebrate Martin's 60th birthday. You know what they say about you, right? That you don't look your age. I think even you say that. So I'm going to talk about how to use excluded middle safely so that there are no unexpected consequences of doing so. And one of Martin's former students informed me yesterday that he's allergic to excluded middle. So I think this talk is on topic. I have no idea where he got that from, the allergy. Anyhow, but before I continue, I'd like to show you what included middle looks like. And
Oh, yes.
Turn it on.
Yes, exactly.
This is what I tell my students. The first rule of computer science, turn things on. It solves 70 to 80% of all the trouble. Let's see. Here's a picture of included middle. So since it's not Alex's turn quite yet, I'm going to talk about the other guy. So this is a picture of the three of us when we were a tad younger. Yes. It's at CMU, there is a bench that says AM Turing. There's another one that says John von Neumann, I think. This is the one we picked to take the picture. And I always felt very much included by both Alex and Martin. And Martin, I think I met when he visited, you must have visited CMU at the invitation of Dana Scott, maybe. That was when we, 1997. Yeah, 1997. Yes, I know you stayed at my place. I did a lot of secondary smoking on the porch discussing topology. But this picture is from 2003 meeting of the Association of Symbolic Logic, also in Pittsburgh. It might be Steve Audi. I no? Well, I can look through the other pictures. Maybe we can deduce something later. Anyhow, my first academic invitation as an academic visitor was also then extended by Martin. I visited Birmingham, not shortly after this, where I did more secondary smoking, this time outside of the computer science building with Thomas Streicher and Martin Escardo. It was a very productive time. Okay, let me get to the talk. So what does a typical use of excluded middle look like? So you'll find people state theorems like this. If excluded middle holds, then something. Now, what is the problem with this? The problem is that if you state it this way, then the statement is going to be vacuous in any setting that invalidates excluded middle, because then you're just proving false implies anything. So that is not very good. In fact, excluded middle is not the only kind of thing that we do which has this problem. You could flip the coin and consider a more intuitionistic theorem of the kind if all functions are continuous, and then you're going to have the exact same problem again, because any model that invalidates the statement all functions are continuous is going to be vacuous. So I would like to address this and fix the problem somehow. And there is an obvious solution, because what actually happens in such proofs, almost without any exception, in fact, I am not aware of any exception, is the following. So here's the question, right? So how to reason? We want to reason relative to a principle such as excluded middle or continuity principle, but in a foundation that maybe invalidates it, and we still want to have meaningful statements. Yes?
But you mean in contradiction or not valid?
I will clarify exactly what I mean. No, in a minute, okay? Yes. So what I mean is, so actually I can say now, so there are reasonable foundational systems where not excluded middle is true. And if you are in a setting like that, then this is not doing anything. Okay, so What did I do? I moved the slider, okay. Okay, so let us first clarify an important difference here, which is the following. So reasoning principles are, when they're usually written as universally quantified statements, especially in higher order logic or topos logic or in type theory, the natural way to state them is as universal statements. I'm not going to go through all of them. All you have to observe here is that there is a for all in the beginning. But then, as I already mentioned, where is the slider that I keep moving? Show me.
So this thing should be up, but it was up.
Okay, I'll hold it like this. So a typical proof uses just some instances. So the way we phrase the theorem is say, oh, we've excluded middle holds, but then we just use some instances of it in the proof. So what's going on? Well, we are observing the difference between claiming that something holds in its universal form versus that we have a schema, right? So in fact, that would be one possible solution, is to say, okay, don't assume universally quantified statements like for all P, P or not P. Instead, what you should have is you should have a schema. So every instance becomes an axiom. This is fine if you're a logician, but if you're going to formalize things, that is not going to be easy because that is a meta-theoretic device. And meta-theoretic devices are not so easily formalized. It's much more convenient to do something that is properly internal and does not resort to meta-theoretic logical machinations. So I would like to explore a different possibility, which is to use modalities and say what we can do with that. And I think it works nicely, and so let me tell you about it. So here's the idea. I'm going to think about principles which are not purely intuitionistically valid, or where there may be somewhat in the air, as oracles, so as abstract oracles. So I'm just going to say that an oracle is a predicate, and I'm putting down omega there. If you're a type theorist, that's omega, that's a shorthand for prop. And so anyhow, so we think of a predicate P from A on a set or a type A as follows. We can ask, let's say we get to ask questions. So elements of A are the questions that we ask. And then we imagine that there would be an oracle, and getting an answer to the question would mean that we are assured that P of A holds, or if you want a more constructive reading, that we get evidence of P of A. So what would a typical example look like? Here are two examples. So the excluded middle oracle would be the one that decides propositions. So you would ask a question, which is some proposition S. I'm not using P because I already have a P, so I'm using S. So the oracle, we ask the oracle the question S, and the answer that comes back is S or not S. And so then we can act on that. So we, for instance, can look at both branches to see which one we're going to take. Okay? So that would be the excluded middle oracle. And a classical oracle, in the sense of computability theory, in this setting, would go as follows. You want an oracle for a subset S of natural numbers. So your predicate is on the natural numbers. You give the oracle a natural number, and then the oracle decides whether n is in S or n is not in S. So it's really just an instance of the previous oracle, but we can easily incorporate classical oracles. And if you go back, all the principles on the previous slide can be rephrased this way because they're all universally quantified statements. So they're going to give you such predicates. Okay. So now we want to define an oracle modality which expresses the fact that we are going to reason relative to an oracle like this. So we're going to say that the oracle modality OP, so that's the oracle modality induced by such a predicate P, is a modality on propositions. And intuitively, we want to read it as follows. We want to say, to establish some statement S using an oracle, so in the modality OP, means that we can either just prove S without consulting the oracle, or we consult, or there is a question that we can ask such that when we get the answer, we may proceed recursively. And we should read this definition inductively. That is to say, you cannot just keep asking questions. You have to eventually stop asking questions and actually produce an answer. So eventually you have to land in the other branch. That's Ingo saying what?
Super cool.
Super cool. Thank you, Ingo.
The largest subtopos of sets is.
Okay. So a little more formally, how do you get this? Well, one way to get it in a topos, say, because there we have impredicativity, we can construct it as the least fixed point of the map that takes a proposition R to just this thing, S, or there exists an A, P of A, R. This is obviously a monotone map because R appears in a covariant position. And so when you do this and you write down what the least fixed point is, you actually get a formula that is well known, at least to some people here, I would imagine. So this is the formula that, if you read it, it's just Tarski's fixed point theorem. It says for all R, it just says that this is the least fixed point of that statement. But I rearranged the ORs. I got rid of the ORs, just write everything using implications. And so this formula also appears in various places. On the next slide, I'll explain its significance. But I'd like to know who was the first person who wrote it down. It appears in Martin Heile's paper, but I don't know. So I'd like to know. Okay. So yes. I see there is a parallel universe in the bottom corner here. Yes. Okay. No, Paul, I think you're off the mark there. So now, if you're a type theorist, then you might do this as a higher inductive type, and then you'd get the following constructors. So you would say the S would just say, oh, we prove something directly. So I can just give a proof of S. And the other option is that you ask a question, so then you have to specify what is the question, that's the little a, and then you have to say, how are you going to proceed once you get the answer? And so this would be some kind of trees, but because we want to work in propositions, we have to throw in propositional truncation. I forgot to say at the beginning that this is, of course, okay, I'm going to do it now. This is joint work with Daniel Achman, but also I have benefited greatly from talking with Andrew Swan, who is somewhere and is giving the next talk, and also with Sevon Park, who is a postdoc now in Ljubljana. So there's like a little group of people thinking about this. Okay, let me go on. So these are the two ways that you could define such an oracle modality. Now, what are some of its properties? So first of all, you have to check that it really is a modality, by which I mean it's a monad on propositions. So it has to satisfy the usual laws. It's monotone, inflationary, and idempotent. So that's an exercise. And the formula on the previous slide is known as the formula that that gives you the least modality forcing a predicate to be true. So because that's a known formula, so OP will in fact be the least modality that forces for all A, J of PA. And so here we see that we really are making every instance true. We're not making the universal statement for all A, P of A true. J, this modality will force every instance separately. Yes? Oh, yes, this goes by many names. This is the same thing as a Levier-Tierney operator, J operator, local operator. It's all of those things. But I call it a modality here. I think in type theory, these things tend to be called modalities also. Martin has been doing lots of type theory lately, so I'll humor him.
Called
Oh, oh, there you go, nuclei. Yes, that's one more name for them. Okay, thank you. So because we know that OP is the least operator which forces a given predicate, then you get an easy formula to check when is one of these modalities below another one, which just means in the pointwise order. Yes, 5 minutes, you're kidding. Oh.
I told you, I'll put my hand
Oh my God, okay. And okay, so thank you. So then let's observe the following. It might be the case that there is an instance of a question where P of A is actually false. So there is nothing that the oracle can answer in that case. Well, in that case, you're going to get a trivial modality. And so that's what we can observe. But importantly, it may happen that OP will be non-trivial even when not for all A P of A holds. And here is an example. So define the LPO modality to mean that you ask the oracle, you give the oracle a sequence of sequence of bits, an infinite sequence of bits, and then it tells you whether there is a 1 in there. So in the effective topos validates not for all F LPO of F because there is no halting oracle. But if you calculate what this means in the effective topos, you're going to see that it means that phi is realized relative to the halting oracle. So it is the thing we want. I think this shows that at least in realizability, we're going to get the correct or the intended interpretation. Okay, so here are a couple of theorems. What can we do with these things? So first of all, let me observe that every modality is an oracle modality. So given a modality J, you can ask your oracle, so you set things up like this. You can ask oracle to show to you why a proposition which is J true is true, and you're going to get back the original J. It's an interesting observation. Some things are easier to describe using oracle modalities than just nuclei. For instance, if you have a family of oracles, then you can calculate the supremum of the induced oracle modalities as simply an oracle modality where you just sum up all the oracles. So that gives the supremum in the lattice. So I think that's also a useful formula. It might come in handy. Okay, so let's go back to the original way of doing things where we just assume the universal statement. Well, if you just assume the universal statement, then we're actually using the open modality. The open modality for proposition P is just P implies S. And so we always have that the oracle modality for P is below the universally quantified statement P, the open modality for the universally quantified one. So we are weakening statements, strengthening statements when we use the oracle modality instead of the old unsafe thing. And then there is a characterization of when the reverse happens, and I'm not going to go through this now. Let me just say that it's a kind of I can explain it in terms of a kind of a drinking game and the drinker's paradox. We often state, as I said, I started at the beginning, we often state that just the universal statement implies something, and then give a proof that actually factors through the oracle modality. And as I was writing these slides, I had conjecture, and I thought, well, that's not accurate. So I'm introducing a new kind of statement that the mathematician can make, which is neither a theorem, nor a conjecture, nor a question, nor a problem. It's a provocation, okay? So here's a provocation. In type theory library, all proofs using lem actually factor through this modality. Okay, one last thing I'd like to quickly have a look at, this is very preliminary work, is can we do something about sheaves? I'm basing this construction on the work of Mike Schulman, Bas Pieters, and Egbert Ricke on modalities in type theory, where they have several constructions of localizations. And something like this, and maybe it's not quite exact, would be the sheafification of a type with respect to an oracle. So the way we think of it is, think of it as kind of computation trees, but there is an equation. So you can either give an element, red, it just gives you an element of X, or you can first ask a question, and then once you get the answer, you are going to proceed recursively. And then there needs to be an equation that says that what element we are coding doesn't matter on what questions we're asking and what answers we're getting. So everything has to be kind of invariant with respect to the questions we're asking and the answers we're getting. And so we might be interested in how to describe the fact that X is a sheaf, especially in type theory. I think that would be useful. So one way would be to say that it's an algebra for the sheafification monad. That would be one way. And so you would get something like, you'd get an operation H, which satisfies the equation that if you give H the unit, then you get back the element. And you can think of H as some sort of a handler in the sense of computational effects, which extracts elements from the computation tree. If you think of that thing as a computation tree, then somehow H is able to get the elements out. But notice that if we're asking hard questions, if this is like excluded middle, it might be actually quite hard to get to a leaf because you need to decide instances of excluded middle to climb up the tree. So so a type equipped with such algebra structure is going to be very special. Okay, to finish up, Tom hasn't stood up yet, so that's very good. Okay, so the last slide is very preliminary. The rest is mostly formalized in Coq. An interesting direction to explore would be non-propositional oracles, so oracles which are not just predicates. Here's one that is very relevant. This is also how Lean formalizes choice, is that you have an oracle, and the way it works is you give it a type A, and you know that A is inhabited, and then you want the oracle to produce an element. So this is going to give you choice, but this is not propositional, so it's going to bring in extra complications. And let me also just say a little bit about it's just one more slide. Thank you. It's just related work, you know. Here, I can tell you what the related work is. So there's a paper which I already mentioned by Egbert, Mike, and Bas on modalities in homotopy type theory, which discusses the general theory of modalities in type theoretic contexts. And I got a lot of material from that. Andrew actually worked on oracle modalities already. He took it in a slightly different direction. He studied several things related to oracle modalities. I think it was in cubical assemblies also. So that's a paper that's it's a very nice paper. I recommend everybody to read it, and I recommend Andrew that he publish it. Oh, Swan with a W. I'm sorry about this one. See this W? It threw me off, so the next one is also, yes. And I should also just say that if we calculate what these oracles are doing in realizability models, we get precisely the gains of Takayuki Kihara that he used to describe Levier-Tierney topologies in the realizability toposes. So that's another useful connection. Thank you.
Yes, Steve.
In a topos, the modalities form a distributive lattice, and the open modalities have Boolean complements, which are just the closed complements. So there's some excluded middle that actually works as long as you realize that the negation of something is not a sub-object of one, but it's well, actually, it's going to be a stone space. So it's not an object in the. So when you're working point free, this actually is quite a useful principle. You can use excluded middle if you're trying to prove that some modality is the top modality. So you prove it has both the open and its close complement, then you know it's the whole thing. So that looks a bit like excluded middle. In fact, we've been using this in the point theory and that.
So that's an interesting thought. If I understand you correctly, that's kind of an excluded middle at a different level. It's in the lattice of nuclei, right?
Yes.
Yes. Okay.
Is that the same thing as just working in the cover, where you're working in the topos, where you replace omega with the lattice sheaves on that? Seems kind of equivalent. You just replace your propositions with.
Is it possible to express this modality? Sorry, is it possible to express this modality by saying that there exists a list of things in A, such that if each thing in the list satisfies
Yes.
then satisfies the proposition, then this thing, then that proposition is true.
This intuition comes from the fact that you can think of the modality as building a tree, and if you go up a path, then you're going to get to your answer. And by going up a path means that you ask some questions and you got Oracle to answer them, and so you want to collect them. But this is prevented by the propositional truncation. You cannot construct such a list unless you have some further special properties. But one of such further special property, which is important for the realizability models, is that if you use not a proposition but a container, and that container is projective, then you can lift. You can get yourself out of propositional truncation, and you do get such lists, but only under rather special conditions. But these conditions make sense computationally.
So what I said is too strong in general.
Yes.
But
it
okay in
works
some cases.
In some important cases.
Okay, thanks.
Do you have any recommendations for how one might work safely with excluded middle in a predicative setting?
You mean, I suppose you're alluding to the fact that if you're very predicative, you might have a hard time constructing such a modality. I don't know. Find a way to construct such a modality, and my answer is based on the fact that I know that it's the least one that forces the thing that you want to pretend is true. So you have to find some way of carrying out that forcing. And so, maybe modality is not the only way. You could go back to some sort of schema or something like that and do something that is going to look a little bit different.
Very quickly, maybe.
Okay.
How quick? Okay. So I want to think about the provocation. So, so in type topology, there are some statements that are equivalent to excluded middle. How does your modality say something? Also, you said that this is vacuously true, but I'm thinking in the free topos, where excluded middle is not false and is not true. And so an implication of excluded middle into something else actually is doing something.
Right. So in a specific setting, such as the free topos, such statements may be quite reasonable. I'm trying to be very conservative and make them reasonable in every setting. But to answer the question of what happens when you're showing that one principle implies another principle, those are usually implications between universally quantified statements, and experience shows that those are instance reductions. So you're actually just asking your oracle a single question and then you complete in most such cases. So that's a second provocation, is that in fact, when you're proving one universal statement implies another universal statement, you are going to use a very special case of this where you're asking the oracle precisely one question. And that's called instance reduction. So
More about
yeah.
Thank you.
Okay, we should really move on. Thank you.